Okay, in section 7.2, direction fields and Euler's method. Okay, so let's start with this graph that I have right here. Let's suppose that I know that the integral function has a graph that looks like the following there. So what I do is now I have a starting point. And let's just say that I know one point on this graph. So I'm just going to create one point that's on that graph. Now, using my derivative function, I would know the slope at that point. Then I can generate an equation which gives me a graph, and that graph would then look like the following, because if I'm creating that graph, there is my graph. Now, I can step over at a very tiny distance on either end of that point. But all of those points are in an interval, okay? And that interval, okay, is starting, let's say, okay, here's that point. So this interval is in between these two red lines. So that's that tiny interval. And so all these points in this little interval closely approximate the graph of the interval function. And so if I step over to the right and say, okay, this point is approximately on the graph. So if I have another point that's approximately on this graph, I know I can use my derivative function to get the slope of the line containing that point. So now what's going to happen is I'm going to end up having a new line here. And then I can step over and say, okay, there's an approximating point again to the right here. And then approximate the point on that integral function. And then I can continue to keep doing this over and over again. But those slopes are going to change depending upon the derivative function. So now, unfortunately, it's impossible to solve most differential equations in the sense of obtaining an explicit formula for the solution. In this section, we show that despite the absence of an explicit solution, we can still learn a lot about the solution through a graphical approach, direction fields, or a numerical approach, which is Euler's method. Now, what we just discussed earlier was a direction field. So suppose we are asked to sketch the graph of the solution of the initial value problem. We don't know a formula for the solution, so how can we possibly sketch its graph? Let's think about what the differential equation means. The equation y prime equals x plus y tells us that the slope at any point xy on the graph, called the solution curve, is equal to the sum of the x and y coordinates, and you can see that from figure 1. So here we have point x1, y1, and there's your slope. And then we have another point, x2, y2, which is the slope. So we've created these two lines. And again, it's going at the direction of what that slope is. Now, in particular, because the curve passes through the point 0, 1, its slope there must be 0 plus 1, which is equal to 1. So a small portion of the solution curve near that point 0, 1 looks like a short segment through 0, 1 with slope 1. So if you look to the right here, okay, when we add those two values, 0 plus 1, we get 1, and that's what our slope is going to be. It's a positive slope, and it's that little segment. So beginning of the solution of the curve through that point. Now, as a guide to sketching the rest of the curve, we would draw short line segments at the number of points x and y with the slope x plus y. And the result is called a direction field, and it's going to be shown here in figure 3. So for instance, if we look at the line segment at the point 1, 2. So here's our graph, here's 1, and there's 2. Okay, so we're looking at this particular point right here. Okay, now that slope is going to have the value of 1 plus 2, which is going to be 3. So that little line, that segment, has a slope of 3. So the direction field allows us to visualize the general shape of the solution curves by indicating the direction in which the curves proceed at each point. So if you take a look at figure 4, it says we can see the sketch of the curve and it's going through the point 0, 1. And by following the direction field as in figure 4, notice that we have drawn the curve so that it is parallel to nearly line segments. So what you see here is that you have this particular curve, and then once it hits that point 0, 1, you can see that this curve is following what that slope would be, or that little segment would be, because 0 plus 1 would be 1, and therefore would have a slope of 1. And then that is telling us the direction of what that is going to look like. So in general, suppose we have a first order differential equation of the form y prime is equal to f of xy, where f of xy is some expression in x and y. The differential equation says that the slope of a solution curve at a point xy on the curve is f of xy. If we draw short line segments with slope f of xy at several points xy, the result is called a directional field or slope field. These line segments indicate the direction in which a solution curve is heading. So the direction field helps us visualize the general shape. So I'm going to go ahead and open up our example here. Okay, so this is the function f of x plus y equals x plus y, which is what we have in our example. So here are x values. We have like x minimum values, x maximum values, so it depends on what it's going to look like depending on the value of x. And then we have our y-axis values, the y minimum, y max. Then we had number of sample points. So if you take a look at the x minimum, okay, if I shift it to the right and I keep getting larger and larger with the value of x, okay, you can see what's happening with the directional field. So if I start here at -8 and I continue, you can see what's happening with each particular line segments. They start changing according to the slope. Okay, likewise, if I look at the x maximum, I'm going from 1 to 2 and 3 and 4, and again you can see that the line segments are changing according to its slope. For the y values, what's happening here is that you can see that the y values are shifting it either up or down, but again you can see what's happening with those line segments around that space. Same thing with the y max. Okay, now if we display the points, that means that every point on this graph has a line segment, and that line segment is depending upon what that slope is of that ordered pair. So if you have an ordered pair here, which is this is 2, and then you have 4. Well, if the slope here is 4, if this line segment has a slope, well, if you look at this ordered pair, it would be 4, 0. If you add 4 plus 0, then that means that's going to be the slope of that particular line segment. Okay, so the demonstration generates a slope field for a number of differential equations. You have the option to plot a particular solution passing through one point. And then you can control again the x and y axis as well as the number of segments plotted. So that's what a directional field looks like.